following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Okay, ready for today's discussion, which I am quite sort of happy about. I hadn't really seen this coming, but I realized that first, we haven't said anything about how do you estimate the error in a problem. Because we're often taking a continuous problem coming from differential equation typically, and discretizing it, and we want to know, and solving the discrete problem, we will want some idea. It's not just some math question, of course, because in engineering design or analysis, an idea of what the error is critical. And secondly, it gives us an idea of where we can improve it. If we see what's controlling the error, then we know what's going on. And so I'm speaking now about steady state problems. We discussed error for initial value problems. And we realized there that the error depended on, usually finite differences. So the error we knew we could figure out locally from the finite difference that we chose. We chose second order accurate differences frequently, but we could have moved up to fourth. And then the other ingredient you need is stability to know that those local errors don't explode as time goes forward. Okay, so that we had something to say about error and accuracy at that time about that topic. And now I'm realizing that many of our other topics fall in this category, and I've put three of the topics here in the idea of sort of where the underlying discretization is a projection, is somehow a projection between the true solution and the discrete computed solution. Somehow the discrete computed solution is in some family of some finite dimensional family where we can compute, and we're projecting into that family. And here are three examples, so you'll see that actually what I'm talking about is central to the whole semester. Well, finite elements actually appeared more in 1808-5. So I'll have to recap a little bit there. But they would be the natural tool for solving that list of continuous problems from calculus of variations that I talked about last time, minimizing some energy, where the energy is typically an integral, and we're in the continuous case. And what's the finite element central idea? It is choose these guys, choose some basis functions, and look at their combinations. Maybe choose n basis functions. I guess I better get a chalk or it's going to be a short lecture. Okay, so this is we have a continuous problem, continuous ordinary differential equation or partial differential equation with boundary conditions as always that we want to make discrete. And the point is, I am not making it discrete by finite differences. This is the different root from finite differences. And in Laplace's equation and these and many problems, this is the preferred root. And it's finite elements are a particular choice of these guys. The Galerkin idea, so I'll use his name for the overall idea, is choose these and look for the best combination, and we have to say, what does best mean? Well, best is going to mean, in our minimization problems, it will be the combination that gives the minimum. the combination of these n trial functions. Now, the exact solution is not going to be in that little n-dimensional space. Those functions for finite elements might be piecewise linear, or if you want to upgrade it, they might be piecewise parabolas, piecewise cubics, whatever. That was the brilliant finite element idea, to choose simple functions. And then you could take n quite large, but you're still not getting the exact solution, of course, and it's to estimate how far off you are. But then also in multigrid, what was the idea in multigrid? We started with a system at level h. We started with some problem AH, UH equal FH, which was a big system. If we did ordinary Jacobi or Gauss-Seidel, that was too slow. The multigrid idea was project, there's that magic word, project onto a coarse grid where the problem is smaller. Here we started with a continuous problem and we got it down to size n. Here we start with a discrete problem and we cut its size in half or in quarter or in eighth again. So we're always, projection is producing a smaller problem, and the question is, what are you losing? And actually, conjugate gradients. There the spaces, you remember these spaces? The spaces span the combinations of B, AB, A squared B, and so on. That was the computationally convenient space of subspace to project onto, and so you know, we've got important examples. Now, what I realize, I'm pleased about this, that they all fit. So here's my problem. What's the error? So I'm going to use U star for the correct answer. This is the truth. And I'm going to use U star, capital U star, for the approximate. The one that we get by any of those key ideas in numerical analysis. And I'm trying to estimate the difference. Okay. And I just put up here that I'm dealing with positive definite problems. In fact, the matrix K, that the symmetric positive definite problem that you have, often has this A transpose CA form, or in the continuous case, it might be K might stand for the A transpose, might be minus the derivative. The C might be a variable or constant, physical coefficient. A would be d by dx. That would be the K thing. If I apply K to U, the equation I want to get is KU equal F. That's the strong form. Strong form will be KU equal F. But the whole point of last lecture and this one is that we don't get to the strong form. This projection starts with a minimum problem and gets to a weak form. And it's the minimum problem or the weak form that we want to think about, not the strong form. Okay, now, up there I wrote an identity. If you just multiply that right-hand side out, I believe it comes out right. And it's very valuable for our purposes here. Okay, so what's on the left side? This is the quantity that we're minimizing. We're minimizing this. And by just manipulation, we wrote it this way. So now I can identify what U star is. So I'm going to minimize this over all U. This certainly looks like a discrete problem, right? So think of U as a vector, F as a vector, K as a positive definite symmetric matrix. Just think about that, but I want it to apply very much to the continuous case too, to differential equations. But here's the point then. What's the winner? You can't immediately see, well, maybe you can somehow see that the derivative, when I set the derivative of this thing to 0, I get that equation. You can kind of believe it, even if it's vectors and matrices. But here you can see right away that how do I make this small? This is a constant here. That's just a constant, so it doesn't depend on U. So what choice of U makes that term small? Well, of course, it's the choice of U is the one that makes this thing 0. Because that's a positive definite matrix. No way anything's going to get negative here. This is a something transpose K something. You remember what positive definite means. It means that X transpose Kx for every vector X is never negative. So the best we could do would be to bring this to 0, and of course to bring it to 0 is to bring the X to 0, to bring this thing to 0. So it's this thing should be 0. So U minus K inverse F should be 0. And of course, that leads us back to the same conclusion that we reached from the strong form. Okay, good. So that's an identity. But now I want to use this identity to answer the question about what if I minimize only on a subspace. That's the problem for today. So that's the question. Maybe I write it on this fresh board. Now I minimize only over some subspace. Now can I use capital U I used little u for in here allowing it to be any vector. And I found the winner. And let me give the winner a name. U star. It's a real headache in this subject of just the notation. What should we call the winner? So sometimes I called it U hat that was a familiar notation in estimation theory, least squares. Today I'm going to call it U star. So it's U star is the winner, small U star. Let me take time out, 1 minute time out on a board that I'm going to, optimization is about the problem of minimizing some function f of x. I'm just going to take 1 minute on the problems of an author. What do you call the winning function? Winning vector, or the winning x? It could be just a scalar. We could be doing just calculus. What do I call the x that gives the minimum? You may have a favorite. You can't call it x, right? Because that's just confusing it with the variable x. So I'm saying, well, you could call it x hat, you could call it x star, you could call it capital X. Sometimes so I'll just write a few of those down. X star would be a possibility, x hat would be a possibility, x minimizing would be a possibility. I'm doing this just because I want to write down the thing that you often see, which is arg min of f of x. And I write that down just so that if you ever see it, you know what the heck it means. It has the same meaning as any of these. I am not a big fan of that. But of course, what does this mean? It means the argument that gives the minimum of f of x, right? Argument is a fancy word for the variable in the function. So this is the argument that gives the minimum of f of x, and that's what we're looking for to name. But I'm sure not happy about writing that name down. So I'm not going. Here it goes, disappears. But but you'll see it, and now you know what it means. Okay. Okay. So now this is now the central issue here. I want to minimize my same guy, 1/2 U transpose K U minus U transpose F, or which is exactly the same, that same right-hand side, because the two are equal. I want to minimize over some capital U's, not all U's. If I minimize over all U's, then I get the exact answer. But the idea of all these numerical methods is minimize over some finite dimensional, smaller dimensional subspace of trial functions. I don't know. I'll say minimize over U in the trial space. Just to write it out in words. Okay. Okay. So now I guess my name for the winner in the trial space is going to be U star. So the winner in the trial space is U star. So that's my finite element solution, my conjugate gradient solution, my multi-grid solution. All these problems are reducing to a smaller trial space and picking the winner there, computing the winner there, and then the question of today is how far apart are the two? Okay. So, and now there's this little formula gives us a good idea. This little formula gives us a handle on that. So now the point is that, so okay. So now, can I look at this formula? Maybe I'll copy the formula here. This is the minimum over all these trial guys of 1/2, but I'm going to write it that way, of 1/2 U, that's my trial guy, minus K inverse F, that's my U star. Now, am I okay to give that name to K inverse F? Yeah, I already gave it, I guess. U star is K inverse F, so that's cool, shorter and better. K, transpose U minus U star, plus a constant. So I can forget that. I can forget this constant part. That's not important to us. So this simple identity then has expressed our key discretization approach here as finding the U, and we're going to call it U star, that's nearest to U star. That's the great fact that makes the whole subject pleasant. Okay, so the winner, U star, is then, by this, since I'm minimizing that expression, it's certainly the nearest in the K norm. It's the nearest weighted by K. Somehow that K is important. That K is reflecting the problem we're solving. That K is the energy or whatever to U star. Okay. That's the great conclusion. This is you could say that's the fundamental theorem of this projection error estimate stuff. So do you see that we got to that? The thing that minimizes makes this as small as we can. So nearest Nearest is simply a translation of what that says. Pick the capital U that's closest to U star. Okay. Now, how does that help? That helps because I want to estimate the difference. So now if I estimate the difference of U star minus U star, the simple way is, so I'm trying to get a handle on how different those are. How different is so let me take in this case of, say, Laplace's equation or the 1D case. Again, I'm speaking steady state boundary value problem. So U star is the best combination of these trial functions, capital U, and little U star is the exact solution. Well, let me draw a picture here first. So suppose I'm in 1D, 0 to 1. Okay, yeah, let me pick that model problem again. So minus the derivative of C du dx is f of x with boundary conditions. Okay. And I guess if I'm consistent now, I should write U star because it's the winning solution. And suppose the boundary conditions are 0 at both ends, and it does something. Okay. So that's U star. Okay. So that's the continuous case, which I'm drawing a picture to show, to represent what the solution might look like. Okay. Now, what about this finite element stuff? Suppose the phi's are linear pieces. I'm going to do linear finite element method. Then any combination of these linear guys, it's going to be piecewise linear, there's going to be a mesh, you know the setup. You know, it might look like that, and it have a value there, might have a value there, might have a value there, there, and there. Okay. And this, let's suppose this is the winning, doesn't look like a winner to me, because it's, you know, like you think you could probably do better, but capital U star. But remember that we're measuring, what's the K norm stuff? I'm measuring the difference between these two, not pointwise, which would be, of course, pleasant to say, okay, the distance is just, you know, maybe the maximum distance or the mean square error. That would be quite pleasant. But here, the measure of distance involves this K, which comes with the problem. So by distance here, I mean the distance between U star and U star in this. Can I write it with a capital K there to indicate that that's the K norm? That's the norm in which this is small as can be made. And what is the K norm for this particular problem? Well, it's the integral, and involves the C, and it involves the U star prime minus the U star prime squared dx. Integrated from 0 to 1. I'm just picking this example problem so that you get some idea of how we're measuring the error. It's the natural measure for the error. It's the energy measure. We're measuring error in energy. This is an energy expression. This thing, you know, represents some kind of elastic bar or something, which is, so we're measuring the internal energy here. And notice in particular, maybe the most important point is not the C of x, which is just like comes along for the ride. But the fact that we're measuring, our measure of the error is in the derivative. We're measuring error in slopes because those are the stresses in the bar, and that's where energy comes from, internal strain energy. Okay, so in other words, I have this function u star, this curved guy, and I have this function which I'm thinking to be the winner. And again, it's the winner in the sense that it minimizes this. This is the minimum. This is the expression that we have some handle on because we know that u star, capital U star, will make that as small as it can. It does not make small the pointwise error. Finite elements, it might try, it might accidentally, we hope it does, of course, get pointwise error right. But what it is constructed to get right is energy error. Make that small. Okay, so now the question is, how do we estimate the difference? Okay, so now here's this key point. How do we estimate the difference? And so, again, we're looking at the error. By the way, I should have, maybe I did, put a square there. That was the norm squared, but of course, minimizing the norm, you realize why I don't want a big square root sign, it's just clumsy. So I'm looking at the square there. Okay, so now how do you estimate the thing? How do you estimate the thing knowing that this piecewise linear that came out of some finite element calculation or some giant code is best possible? Well, here's the idea. Look at a convenient candidate that might not be the winner. Let me put, because this was as small as possible, this is less than or equal to u minus u star, always in the correct measure, for every trial function u. This just says what I've said now 3 ways, that u star is the best in the k norm. Now, so to get some bound on this, I can take any u. I can take any u and estimate its difference from u star, and that will give me a bound. In other words, I don't know what this particular guy happened to be, but I know it's better. Let me just jump to the key idea. I know that that one is better than the one, and if I had a different color, maybe this thing has got another color. Well, okay, here's another color. I know it's better than, for example, I'm just going to pick one function one piecewise linear trial function that's quite convenient. Pick the one that interpolates the exact one. Okay. Now, for some reason, known only to finite elements, that wasn't the finite element winner. That wasn't u star. That was another u. For example, so like I'll put it in blue here. For example, take u to be the function that interpolates u star, little u star, the function that I've drawn here. That gets, since our question is how close can we get to the curved guy by piecewise linear, well, one choice is how close does the interpolate come? It doesn't necessarily come the closest, probably not, but it's in the right ballpark. So now I just ask the question, and let me draw it again, draw the same picture again. I have a function, and I interpolate it by piecewise linear guys. So a piecewise linear function there. And so this is a comparison between U star and U star and its interpolate, which is my candidate U that I'm recommending as a trial. And now it's a pure approximation question. You see, we no longer have to know all about finite elements. We don't have to know anything about finite elements. We're just asking the question, if you give me a function and you compare it with the piecewise linear interpolate, how far apart are they? How far apart? And do you know what? And let me call the step size h. So, and of course, could be unequal steps, could be an unstructured mesh. Everything works here. But now we come just to a basic sort of understanding of calculus. How close does a curve come from the chord? Really, that's what it's come down to. How close is a curved function from a chord? I could even blow that up. So here I have some curve going up, and compare that with the chord. And how far, and this distance here is h. Anybody know? So I'm just looking for something like, is the difference of order h? Is it of order h squared? Is it of order e to the h? What's the distance between the two? If I take a little p, and you could imagine it's a parabola because I'm focusing down on just a little piece. If I take a little parabola, a little h piece of it, and I compare it with the chord, what's the distance between the two? That distance there. Well, your eye probably tells you that it's smaller than h, right? Because h was this big, and I'm only looking this big vertically. So this distance, that distance there, maximum distance, is of order h squared. But that's not the question. The question is, how far apart are these? How far apart are these in this measure? How far apart are the slopes? Because the K norm is dealing with the slopes and not the function itself. So more important than the distance is the error in slope. And would you want to guess what that's like? What's your guess on that? The error in the slope. Now, the slopes are not going to be as good as the function, as always. Slopes are one derivative higher. You lose something, you get order h. So that's the error. Let's see, I hope I'm right here. Yeah, I think that's right. The error in slope. I was speaking point-wise, and then I've got to integrate it over a whole interval here, a unit interval, so I'll still get, well, if I square it, of course, I'm going to get h squared, and then if I integrate it, I still have h squared, and then when I take the square root, I have h. So h is the right quantity. So our answer is estimate, if I can put down here what our conclusion was from this method, by taking capital U to be this convenient, not the only choice, but a convenient choice, just to get an idea of what the error might be, and then the error from the actual U-star has got to be better. Our estimate is order of H for this particular application. This particular application. That's the error in the energy norm, in the slopes. And then we would, so the theory of finite elements would go ahead to try to show that the error in the distance between them, in the displacement, you could say, is h squared. But that's not so easy, and I won't be able to do it here. Why is it not easy to say that the error in the displacement is of order h squared? It's certainly true for this interpolant. No question that the interpolant is you could easily see as h squared, order h squared away from the function. But the point is that capital U star was not the best in staying near the function. It was only the best in staying near the slope. So I don't have this crutch to lean on here. This is in the K norm and not in the mean square norm. It's in a norm that deals with slope and not with just plain displacement distance. Okay, maybe that's made the point, and this is the heart of finite element theory, to do that. Okay, if I could take a minute about notation, because the notation that I've used here of a K is really a matrix notation. It's not true, you don't truly see it in finite element papers. For me, it's clear, right? I mean, that identity was quite clear from vectors and matrices. But with finite elements, I'm really dealing with functions. So it's not fair to use matrix notation when, when it's integrals and derivatives and functions that are involved here. It's, these are functions and the actual solution is a function. So all I want to do is mention the notation that you now see in, say, in 16920, the engineering course that would be, some quite related to this one, of finite elements and Galerkin and all sorts of stuff that we'll touch in the remaining weeks. How would they write the minimization problem? So they would minimize over U, the original problem now, not yet going back to the original problem and just saying, wait a minute, we didn't really have a good notation for it. The thing I'm looking for is a note. It's like this. This is the kind of thing that I want. C of x, U prime squared dx. Well, or it might also have a first order term, a d of x, U squared of x. It could have that. It could have second derivatives. It could be in two variables. For Laplace, we had a minimum of du dx squared and du dy squared, dx dy. Well, and we had the linear term too. I've just written the sort of the left-hand side, the quadratic term. And all I want to say is that everybody, well, not everybody, but a lot of people now would use the notation A of UU for the quadratic term. So that A of UU in an engineering paper represents the internal strain energy, whether it's this combination. It somehow suggests to us it's quadratic. And then there's a linear term, and that's often written L of U. So I better put down what L of U typically is. This L of U might be the integral of f of x, u of x dx. That would be the linear term. You see that all I'm saying, and should I think I'd be happier to have the 1/2 there. So that it's just a match with this, but somehow it's a little cooler by, it sort of isn't quite, this looks so much like vectors and matrices that and that is kind of neutral. Okay. So I'm just speaking about notation here. And I could have mentioned this last time when I was speaking about all these examples from calculus of variations. Okay, so that's the minimum problem. If you give me that notation for the minimum problem, what's the weak form in this notation? So I'm introducing this just because you see it elsewhere, so you better, it's exactly what we're doing all the time, so I just want you to recognize it. Okay, so how do we get the weak form? Can I recap how you get the weak form? If U is the winner, right now I'll just think of U as the winner, then if I move it by V, move it a little, then this expression should go up. So what happens if I move it by V? So I'm going to compare the two. I'm going to compare that with 1/2 A of U plus V, upped a little, minus L of U plus V. And the point is that this guy should be, then I'll erase min and put in less or equal to. I'm just recapping in a new, that this should be less or equal to this one for all V. You see it's the weak stuff? U is the winner. I'm now using U and not U star. And I'm using V for the delta U for the movement away from the winner, which raises the energy. Okay. Now, what do I plan to do? I plan to cancel common terms here and see what's going on and find that first variation. That's just what I did last time. I'm just doing it in this new notation. So what's the point? This L of U is linear. So L of U plus V is the same as L of U and L of V. Right? If I put in U plus V there, it splits into two integrals, and here they are. So when I subtract, these guys go. Now, what about this one? Well, just as last time, when I put in U plus V here and expand everything, now I have something squared. So I'm going to get this business here is going to be 1/2. I'll get something from the U alone, and then I'll get 2 something, time canceling the 1/2, from the U and V. That's the cross term, and then I'll get something from the V alone. Is that, I'm dodging a couple of bullets here to make, just going to the main point. Okay, so the main point is I'm going to subtract, I'm going to look at the differences. So the zero order terms are all gone, and it's this quantity that has to be greater or equal 0, right? I was left with that greater or equal 0 sign for all V. Okay. And what does it, where do I, oh, don't let me leave minus L of V there. I need him. Okay. So that's the thing that has to be greater or equal to 0. Now we're just going to repeat the same discussion as that we had last time with different letters. If this is going to be greater or equal to 0 for all v, then I'm going to think of small v's, in which case this term is going to be smaller than the others and won't help. So what has to happen? What has to happen for this to be greater or equal to 0 for all v? You know, like we're taking the derivative in the direction of v. We're moving in the direction of v. And this is the first order term. That's the first variation. That's what has to be 0 for all v. I guess I can bring it over here if your eye will follow it. I have a of uv plus minus L of u, L of v rather. That's the sort of first order term, and then the second order term has to be greater or equal to 0 all v. And the question is, so what? What do we get out of that? Well, what I'm saying is this stuff has to be 0. Because v could have either sign. So if this was positive or negative, I can choose the v, I can switch sign if I want to, make it positive, make it negative, and so it has to be 0. So a of uv has to equal L of v, and that's the weak form. That's the weak form. That's the form integral of c u prime v prime dx equals integral of f v dx. That's the L of v, and this is the a of u and v. So this is what you see in engineering papers when they're launching into the finite element method and they're planning to look a little, you know, to get some notation. That's a very familiar notation. And then final point is, what about this term? So now we know this is 0. This is the weak form of the equation. Find u so that this holds for all v. That's the weak form of the equation. And that's the form, oh yeah, I better not rush by it. This is the form in which you plug in, this is the form finite elements come from. The finite element method comes from taking, it doesn't solve this equation exactly. This is a differential equation. Come in here, it's our Euler-Lagrange equation. It comes from, the finite element method says, okay, take the trial functions and get it right for those guys. So that gives us our n equations, where this is a continuous problem. Yeah. So this is what just leads you, the weak form is what leads you naturally to finite elements. You take this and you only make it true on a finite dimensional space. Okay, and then the final comment is, what about this guy? Well, the whole point is that we assumed positive definite, we assumed stability, we made our life easy by guaranteeing, by the fact that this is always greater or equal to 0. This is always, I don't even have to think about this one. Okay. Because if u and v are the same, this is a square, and that material coefficient had better be not negative, right? Okay, so that was, thank you for your patience to listen to see this notation for the same thing that we did last time for the weak form, and you see how it pays off immediately to give us the give us the finite element form. Okay, good. So the project ones are all there, and there are just 2 or 3 left here. And I hope you have a super weekend, and do give a thought to project 2. So I've got, well, yeah.